All right, when we last left off, we were talking about the fact that water has a little dipole going from each hydrogen to the oxygen. And we discussed that these dipoles do not cancel out because this molecule is asymmetrical. This oxygen's pulling on this pair, this oxygen's pulling on this pair, and there's nothing out on top of this to cancel out those pairs, so there's a net dipole. What is the name of this shape, though? How do we get a three-dimensional shape from this drawing? We mentioned that we had to count the total number of things on the central atom, which in this case is oxygen. When we look at this molecule, how many things does the oxygen have around it? It has a hydrogen atom and another hydrogen atom. We count the atoms, not the number of bonds the atom makes. And then there is one lone pair here and two lone pairs there. There are 4 total things on this molecule. So as Tyler DeWitt likes to count, there's 1, 2, 3, 4 total things on there. We count each pair of electrons as 1. We count each bonded atom as 1. There are 4 total things. Those 4 total things are made up of B, which stands for bonded atoms. There's 2 hydrogens, so there's 2 B's, and there's 2 lone pairs, so there's 2 E's. And now we want to introduce how you can get the shape of this molecule using the shape sheet. 4 total things, B2, E2. So now we're taking a look at the shape sheet. This looks very daunting when you first look at it, but when you start breaking it down, you'll begin to see that this is all organized to enable you to get the three-dimensional shape of a molecule. The first column we call the total things column. This is Tyler DeWitt's column. The total things are the number of bonded atoms added to the number of electron pairs on the central atom A. So number 1 is telling you count the total things. On the molecule we just looked at, the total things were 4. The next column is the bonded atoms, or B. On our molecule, how many bonded atoms did we have on water? There were 2 bonded atoms. There were also 2 lone pairs. There would have to be. If there's 4 total things and 2 of them are bonded atoms, there must be 2 lone pairs. And we see there are. There's our 2 bonded atoms. There's our 2 lone pairs. Our B is 2. Our E is 2. Our total's 4. So the total will tell us which bracket to look at. The 4, we're looking in the 4. That puts that molecule in what we call the tetrahedral family. The tetrahedral family is the general name for the family that has 4 things on it. If all 4 things are bonded atoms and there's no lone pairs, it's the tetrahedral molecule. So the family names come from the first molecular name in that grouping. So water belongs in the tetrahedral family. 2 for the B, 2 for the E. This is what we call the VSEPR notation, or the valence shell electron pair repulsion notation, or also called the shape formula. The shape formula, it has the standard form A for central atom, B for bonded atoms, E for lone pairs. My B is 2, so I write AB subscript 2. My lone pairs are 2, so I write E subscript 2. And now I have the name of the molecule's shape. Water is cleverly given the name angular or bent. I think we can see why water's angular or bent. These 2 lone pairs push better than the bonded pairs. So if water was linear, it would push those hydrogens down. So if we had a hydrogen out to the right and a hydrogen out to the left, these 2 lone pairs would dominate that space and push those 2 hydrogens downward, and the angle there between them is about 104.5 degrees. And that's what it says right here. The angle between the atoms is 104.5. It's asymmetrical because the hydrogens are not distributed evenly in the space surrounding the molecule. In other words, there's no hydrogen on top to balance the 2 that are down, pushed downward. How do I know that the water molecule is polar? When we come here, the symmetry we can get very easily. The hydrogens are not evenly distributed, and it's asymmetrical when there are lone pairs present. But how do I get the polarity of the molecule? If you remember from the notes, in order for a molecule to be polar, in order for the molecule to have a net dipole, first of all, it has to be asymmetrical. For it to be polar, it has to be asymmetrical. For it to be polar, it also has to have polar bonds. We know water has polar bonds because oxygen is 3,5, hydrogen is 2,1. The difference is 1.4. That is very polar. So that means the water molecule has met the qualifications. It is asymmetrically shaped. It has polar bonds. That means water will have a net dipole, which means it'll have partial negative areas, in this case around the oxygen, and partial hydrogens in this, or partial positives in this case around the hydrogens. We don't have to worry about hybridization right now. But this is how you use the shape sheet. You merely count the total things on the central atom, you count the bonded atoms, and you count the lone pairs of electrons. Let's take a look at carbon dioxide and see if we can use the shape sheet for carbon dioxide molecule to first of all figure out, is it symmetrical? In which case we know it is. There's no lone pairs on the carbon to push these oxygens down or push them closer together. So this bonding pair of electrons, these bonding pairs of electrons here, these bonding pairs of electrons here will repel each other to the maximum distance. If this oxygen starts trying to move closer over here and these electrons go with it, these pairs of electrons will push it right back into the maximum distance they can get apart. This is symmetrical. There's an oxygen here, there's an oxygen here. Symmetry means if you cut it down the middle, in each of the spaces around it, you will find the same kinds of things. So what shape is this molecule? Let's get to that. We already know that the dipole that is going to the right would be canceled by the dipole going to the left. In other words, if carbon was a car and we had a rope on the front bumper and a rope on the back bumper and we had two people pulling with equal strength in opposite directions, the car's not going to move. They would cancel each other out. There's no net dipole. But let's use our shape sheet to see if we can figure out what the name is of the carbon dioxide molecule. First, let's count the number of things on the central atom. Well, I see an atom over here and an atom over here. There are two atoms, and there are no lone pairs. Again, do not count the bonds. Count the atoms. One atom, two atoms. So the total things are two. Total things, two. Two atoms, no lone pairs. How many bonded atoms? Two. How many lone pairs? Zero. So our first column that we're going to look through is we're going to find the two column on our shape sheet, and then we're going to find the shape that has two bonded atoms and zero lone pairs. So here's our two. Our first column is total things. There's our two. Now, what is our B? 2. What is our E? 0. That is the only possibility we have. 2, 0. There is no one bonded atom, because if we only had one bonded atom and one lone pair, we wouldn't have a molecule. We would have an atom, so there's no 1, 1. But there is a 2, 0. It's carbon dioxide as an example. What's our shape formula? Our shape formula, A stands for the central atom. My bonded atoms are 2. And there's no lone pair. So some people just write AB2 and they don't write the E because there are no lone pairs. Or some people write AB2E0. What's the name of this shape? It's linear. What are the atoms? What are the angle of the atoms? It's 180. The angle of the atoms are definitely 180. We can see it right here. Those are opposite sides of the carbon. That angle is a 180-degree angle. It's symmetrically shaped. On one side of the atom is an oxygen. On the other side of the carbon atom is another oxygen. They are balanced. That is a non-polar molecule. When the molecule is symmetrical, it's a non-polar molecule. Whether it has polar bonds or not, it's symmetrical. If it has polar bonds and it's symmetrical, they cancel each other out. If it has non-polar bonds, it's nonpolar anyway. It has to be nonpolar if there's nonpolar bonds. The only way it can be polar is if there's polar bonds. So to be polar, you have to have polar bonds and asymmetrical. To be nonpolar, it can be symmetrical with or without polar bonds. That means there's no partial positives or partial negative areas on the molecule. From that, we know that the molecule is going to have trouble sticking together. We now understand why carbon dioxide is a gas. When one carbon dioxide molecule gets near another carbon dioxide, there's no net dipoles, there's no partial positives and partial negatives for them to stick together. And we're now find out that carbon dioxide is a gas, which is good. Could you imagine if every time you breathed air in and exhaled carbon dioxide, if it was a liquid, you would choke. Let's take a look at the shape sheet one more time. We're just introducing how to use the shape sheet. We will be doing practice problems as well. But right here we have sulfur tetrafluoride, SF4, and this is the Lewis structure for it. And let's use the shape sheet to see if we can come up with the name of this molecule and to come up with whether or not this molecule is symmetrical and are the bonds on this molecule polar or not polar, and will there be a net dipole. Well, first of all, we sort of already know that this molecule is going to be asymmetrical. We have this lone pair right here. And that lone pair is a giveaway that it's going to try to push these atoms into a distorted asymmetrical shape because these push more than the other bonded pairs do. But let's go ahead and look more closely at using the shape sheet to come up with its name. First of all, how many total things are there on the central atom? Counting total things, we're going to start by counting the bonded atoms, not the bonds, the bonded atoms. There's 1, 2, 3, 4 bonded atoms, and there's one lone pair. So that's 5 total things. We count the pair as one thing and each bonded atom as another thing. That's 5 total things. How many bonded atoms are there? There are 4. That means there must be one lone pair if there's 5 total things, and there's the lone pair. So on the shape sheet, we're going to find the column. We're going to start in the leftmost column and look for the 5. Here we go. Here's our shape sheet. Our total things is the bonded atoms B and our lone pairs E. I go down to 5. This molecule belongs in the trigonal bipyramidal family. We take a look back at our molecule, and we see that 4 of the 5 things are bonded atoms, and 1 of the things is a lone pair. So we're going to go to the 4-1. We're going to go to the 4-1. Here's the 4, there's the 1. So I know that I am on the correct line of my shape sheet. My shape formula would be AB4. There are 4 bonded atoms. E1, or I can just write E. Some people do write E subscript 1. You don't have to, and E also means subscript 1. The name of the shape is seesaw. It sort of looks like a seesaw when we look at the molecule. You're like, what do you mean seesaw? Here we go. Right here. Right here. When we're looking at this molecule. If we could see this molecule three-dimensionally, 2 of the fluorines would sort of be down like the stand part of the seesaw. And then one of the fluorines is up, one of the fluorines is down. That's the teeter-totter part of it. So this is what we're looking at right here. It's also called irregular tetrahedral. Why do they call it irregular tetrahedral? There are tetrahedrons have 4 things around them, 4 atoms, but in this case it's irregular because they are bent. Now, the bonded atoms. 2 of the atoms on the molecule are 180. 2 of them have an angle of 90, and the first and third have an angle of 120. We'll demonstrate that more closely in class when we can look at a 3-dimensional shape. And it's asymmetrical. The atoms are not spread evenly about. They are not spread evenly about. We look at the molecule. We don't have anything over here to cancel out those. So, as we mentioned, some of the angles are 90, some of the angles are 120, and some are 180. And we'll take, like I said, we'll look at that when we can see it 3-dimensionally in class. We know fluorine and any other element sharing is going to be polar because fluorine's 4O. In this case, sulfur's 2,5. The difference is 1,5. So the molecule is asymmetrical. It is asymmetrical. It has polar covalent. That means the molecule overall is polar. There will be a net dipole. There will be partial negatives and partial positives.